Um,
Sub 1 with the bar.
so we gotta be a little careful. There's a potential point of confusion here. So let's say that's our function for no particular reason. So if we were to write this as a sum of products, right, we use the min terms. So this is 0, 1, 2, 3, this is M4, or M5, or M7. Okay. If we want to write the product of sums, it's the product of the max terms where the output is 0. So it's actually max term 0, ANDed with 1, ANDed with 2, ANDed with 3, ANDed with 6.
I'm just wondering if for that F you need to put a bar over it, just for notation.
You don't, because both of these are actually the function f, right? This will be 0 in this case, for example. But if we were to write f bar, right, that's what the truth table would be. And we could write f bar equals, min term 0 plus 1 plus 2 plus 3 plus 6. And f bar is also equal to the product of the max terms 4 and 5 and 7. And there's a dualism there, right? This looks a heck of a lot like this. And so you can get to the complement of a function by just switching to the max terms instead of the min terms. But when we write f with a bar on top, we really mean the negation of f. We never use that for just a notation. But if you use a subscript, that can mean anything that you want. So you can say f1 is a particular function, f2 is another function, that kind of thing.
So when we listed the max terms,
Mm-hmm.
we're supposed to list, like for A, the first one, let's say 0, 0, 0, we were supposed to just list A bar, B bar, C bar, or A, B, C?
So for product of sums,
The second one, yeah, for the...
yeah, so product of sums, which is max terms, and let's just stick with f.
Yes.
So the max term for 0, 0, 0 is actually A or B or C,
Okay, good, that's what we were doing.
right?
Okay, good.
And then for the second term, A or B or C bar, and
Perfect.
so on.
Perfect, okay.
And it's not random, but there's effectively a 50% chance you get it right or you get it wrong, right? I mean, if you know how to do it, then you get it right. But if you don't know, sometimes these get inverted and these don't, and it's just backwards from what it's supposed to be. So that's just make a note somewhere, right? You get a sheet of notes for your exams in here, so that's a good thing to put on your notes, right? Maybe just an example of what the max term and the min terms are for a few of these, just to jog your memory. But yeah, you got it right. So other questions on the homework? I can grade it and we can talk about it Tuesday. All right, well, go ahead and pass those in. And again, my apologies that the video from Tuesday disappeared. I don't know what happened. I have one theory that I don't really believe, but I'm running with it. There's a known bug in the software. If your video file is too big, sometimes it just like gets it. And it's possible I didn't pause it in between the first and second halves, in which case it was longer than usual. I don't know if that's reasonable or not. Thank you. All right, any other homeworks coming in? Alrighty, so on Tuesday we were talking about addition, and we looked at making an adder, and the truth table approach to that was combinationally explosive, right? A 10-bit adder would have 20 columns for the inputs and then 11 columns for the outputs, and it's a lot of logic. So we came up with a different approach to doing addition, which is to kind of mimic how we add things as humans, which is usually column by column. And we built this around the idea of a logic block called a full adder. And if you remember the full adder, we had a carry coming in on the right, we had a carry out, we had a sum, and we had two inputs that I didn't leave room for. We'll just call them A and B. Let me do this test one more time for lighting, because there was a question about this. So this is the lighting we've got right now. Here's option B. That seems terrible. And here's option C. Is that enough light to keep people awake when it's 70 degrees in here, 77? Okay, we'll go with that. It's light outside, so I can see what I'm doing. All right, cool. All right, so we have this full adder that basically adds 2 bits. Yes?
What does that say at the bottom?
Sum.
Okay.
Yeah. So we have a full adder that adds 2 bits plus a 3rd bit, which is an incoming carry. Okay, because when we do this addition, right, 0 plus 1 is 1, 1 plus 1 is 0 with a carry of 1. We have to add 3 bits now, right? The 2 bits of our numbers and the possible carry that's coming in from the previous position. So this has basically 3 inputs, and then it generates a sum bit and a carry out, which becomes the carry for the next bit. And so we can cascade these. Feed each of the outgoing carries, get 4 sum bits, and feed 2 pairs of 4-bit numbers into the top. So this might be A0, B0, and so on. And here's sum 0, 1, 2, 3, and a final carry bit coming out. And this original carry in is 0, just like it is over here. And the first digits that we add, we just add the 2 digits without an extra carry. So if we have one of these blocks, it's very easy to build one of these adders. You just hook them up side by side. So our next question is, how do we build one of these full adders? And this will be something you're going to do in a future lab, but we can do it here as a preview. So we know what the inputs are, A, B, and a carry in. So let's just say carry in B, A. And we can make a truth table. And we have 2 outputs. We have a carry out and we have a sum. And now we just got to go and fill in each of these 8 rows. So if we're adding 0, 0 with a carry in of 0, what's the sum bit?
0.
And what's the carry out bit?
0.
Alright, that one was pretty easy. Alright, somebody else, 0, 1, with no carry coming in, what's the sum bit? What's the carry out? 0. I think you got the idea. All right, if B is a 1 and A is a 0, this is exactly the same thing except, right, my bits happen to be in that order, so this will be a 0, 1. But what about 1, 1? What's the sum bit that I'm going to write down here?
0.
That's going to be a 0, and the carry out's going to be a 1. And now we're almost done, right? Because 1, 0, 0, a carry of 1 and 2 0 bits, well, that looks just like, bless you, these two cases, right? The sum will be 1, the carry will be 0. This is 2 1s and a 0, so a 1, 0, 1. So that's going to be a sum bit of 0 with a carry of 1. And this is the same thing in a different order. And then here's the other one we have to do a little bit more work on. So we're adding a 1 and a 1, and we had a carry from the previous stage of a 1. What's the sum bit here? And what's the carry? That's a 1. And we're done. We've written the truth table for a full adder. That's all we need. We can take everything we've been doing up to this point, and we can write equations, and we can turn that into a circuit, and we can build that circuit. So once you've got the truth table, the hardest part is really behind you. So this is the truth table for a full adder. So if we wanted to build this, we could write this as a sum of products. It's min terms 3, 5, 6, and 7. And we can do those in a K-map, so let's do a 4x2 K-map, because we haven't actually done one of those up here. So I'm going to put my carry in and B along here, and I'm going to put A along here. And the numbering on here, 0, 0, 0, 1, and then 1, 1, good. And then 1, 0. And for A, it's just 0, 1. There's no funny ordering there. And we're doing carry out, so we're just looking at this column right here. And so we want a 1 in the following cases, 0, 1, 1. So that's 0, 1, 1. This bit right here should be a 1. Along with 1, 0, 1. So 1, 0, 1. And 1, 1, 0. So that's 1, 1, 0. And 1, 1, 1 is right there. So there's the K-map we want to cover. And we're going to need a rectangle here, because that's the only way we're going to pick up this one on the left. And then do a couple of other 2x1s. So this first rectangle, this horizontal one, what's the expression that corresponds to that in terms of A, B, and C, N? Hello. Yeah, we were up to 77, so. Okay, thanks. So what's an expression for this in terms of A, B, and C, N?
You know, you could take your coat off.
I could, but I might disappear.
BC.
So B, C, right? B is a 1, C, N is a 1, A could be 0 or 1. Okay, so this is B, and I'm just going to call this C. So that's BC. What about this lower 2x1? That's AC. Right? A is 1, C is 1, B could be either. And this upper rectangle, that's BC. And we OR these together. So we have an expression for carry out
That should be A, B, C.
Oh yeah, that's AB. Thank you. So carry out is AB or BC or AC. And there's a nice symmetry there, right? Hold on a second, I'm going to shrink this. That's weird. That looks a little better though. I think my resolution is down, but I can't fix it. All right, so there's an expression for the carry out. Everybody good with that? All right, let's take a peek at the sum. So the sum should be 1 for 0, 0, 1, that's right here. 0, 1, 0, that's right here. 1, 0, 0, 1, 0, 0 is right here. And 1, 1, 1, that's right here. And what do we know about this K-map in terms of covering it? Yeah, it's kind of unpleasant because the only way we can cover these is with a bunch of 1x1s. So using a K-map is not going to minimize this at all. It's going to give us exactly what we get if we just write down the sum of products. And a product of sums will be no better. So that's kind of a bummer because that's a lot of logic. It's 4 3-input AND gates and then a 4-input OR gate. But do you remember what I said about checkerboards and K-maps? I made a passing comment about these. XORs. So what is an XOR? 'Cause I don't think we've spelled those out. I'm going to leave this for a moment.
It's an OR gate that gives you a NOT.
Go ahead. Gives you a not what?
So for instance, if you have a 1 as a conclusion, it's going to give you a 0. If you have a 0 as your conclusion, it's going to give you a 1.
Okay, that's part of it. That's a big part of it. So an XOR is almost like an OR gate, except you're only allowing A or B to be true. It's got to be exclusive. It can't be both. It's literally A or B, not both. So if A and B are both true, the XOR is false. So an XOR means A is 1 and B is 0, or A is 1 and B is 0. Okay, slightly different from a regular OR because of this last row.
Oh, it's not a NOR?
It's not a regular OR,
No,
right?
like
This,
a NOR.
it's not a NOR either.
Oh, okay. I thought that was a NOR, so never mind.
Okay, no, so a NOR is an OR that's totally inverted. Okay, so a NOR would be 1, 0, 0, 0 for the outputs. An XOR is identical to an OR unless both inputs are 1, in which case suddenly the output goes down to a 0. And our symbol for this is our curved AND gate, but with an extra line in the beginning. And our logic symbol is an OR symbol with a circle around it. And so I usually put that inside the XOR gate, and then the output is A. XOR B. And this is the device that's available in your parts kit. It says 74 something, I don't remember what the number is. But it just has this slightly different behavior. And XORs we usually think of as having only two inputs. A 3-input XOR gate we need to think about, because let's just think about XORs as just having two inputs for now. Okay, and it's defined by this table. But let's do the following. So keep this truth table in mind. But let's take 3 inputs. And let's just make a column for A XOR B. So we're ignoring the C input. So just looking at A and B, 0, 0 gives us a 0. 0, 1 gives us a 1. 1, 0 gives us a 1. And 1, 1 gives us a 0. Okay, that's just straight from this truth table. If we take that column and we XOR it with C, so now we're looking at this and this.
Sorry, for A XOR B, shouldn't the fourth row be a 0 middle one? Because both B and C are ones.
We're looking at A and B.
Isn't that A XOR B?
Mm-hmm.
But in the case of the A XOR B, if they're both 1, then out should be 0.
That's here and here.
But in the first 4 rows,
Mm-hmm.
the last row is A B.
A is 0, B is
I-
1. Yeah, so ignore C.
I thought A and C were switched before it was C, A, B.
Oh, okay,
So it's-
okay.
Yeah.
All right, so we agree this is A XOR B.
Yeah. Okay.
So let's take that and XOR it with C now. So 0 XORed with 0 is 0. 0 XORed with 1 is 1. 1 XORed with 0 is 1. 1 XORed with 1 is 0. 1, 0 gives us a 1. 1, 1 gives us a 0. 0, 0 gives us a 0. And 0, 1 gives us a 1. And that's the same truth table as our sum column for our full adder. So this observation, which took, quite a bit of time just now, but which you'll start to recognize as you work with these truth tables more. This observation that this is the same as this lets us write the sum as a couple of exclusive ORs. It's going to let us say the sum is equal to A XOR B XORed with C. That's where C is the carry in. So we don't need all the logic of the whole product of sums or sums of products. If we have some XOR gates, we feed A and B into 2 of those inputs. And then we feed C into another one. And there's your sum. Kind of making sense? So that's a really long-winded derivation, but it comes from this idea that when we drew the K-map, we had this checkerboard behavior, which if you try to cover, you get these really long equations. But when you get to that point, take a step back and say, wait a minute, maybe there's an exclusive OR of some type going on here. So make yourself a truth table for an XOR of however many inputs and see if it matches. And if I had a 1 0 0 1 0 1 1 0, in other words the exact opposite checkerboard of this, that's no longer an exclusive OR, but it's just this complemented. So I could take my final output and just throw it through an inverter and I'd have my circuit. So if you have some kind of checkerboard pattern, there's a good chance you can use an XOR to simplify it, but it's a trial and error kind of thing. Especially if you have a 4x4 and the upper half has a checkerboard but the bottom half doesn't, right? You're going to have to play with it and see where the XORs go. Yeah?
It just replaces the sum logic expression, not the carryout.
So the carryout we found using the regular sum of products, right? And the K-map for that was a nice, well-behaved. But for the sum, yeah, we can replace the sum with either the full expression for this or with the XORs. So the whole full adder is 3 2-input AND gates, a 3-input OR gate, 2 2-input XORs, and that's it. It's a lot, but it's not all that much. It'll take a good part of your proto board, but it's not totally horrifying. So your next lab, which we'll talk about on Tuesday, part of that's going to be implementing a 2-bit adder. Now this is one full adder. Theoretically, to make a 2-bit adder, you're going to need 2 of these circuits, right? That's going to be a lot of hardware. So we're going to find a way to short circuit that and not have to actually build 2 of these things. But think about this for a few more seconds and let me know if you have questions on this. We still have a video recording going, so that's good. All right, so let's finish this up. You want to make a 4-bit adder or a 100-bit adder or a 2-bit adder even. And we said we can take these full adders and just sort of chain them together side by side. But this one particular full adder has a slightly easier task than the others. Because this first carry in that I'm sending to it is always a 0. Right? When we add 2 numbers, those first digits, we implicitly have this carry in of 0. So this doesn't really need the ability to deal with a carry in. In some sense, this is the actual truth table we need to implement for just that first stage of the full adder. Right? Since we know the carry in is always going to be a 0, we don't need to build any logic to deal with any of this stuff on the bottom where the carry in is 1. So we can build a different kind of circuit for this very first block, one that completely ignores carry in and just takes in 2 bits A and B and generates a sum and a carry out. In other words, since we know the input is 0, we can just eliminate that input. And that's a much simpler circuit than a full adder. Mm-hmm.
Instead of eliminating, do you mean connect ground to it?
If we connect ground to it, it will work if it's got all of the circuitry inside. But no, we're just going to eliminate it. We're going to build a totally different unit, which is going to look like this. We're going to have a block have A and B. We're going to have a sum, and we're going to have a carry out. And our truth table is going to be the following. Right, and that's just the top half of our original truth table. And if we write equations for this, who can come up with an equation for C out in terms of A and B? Yeah, it's just an AND gate. How about for the sum? That's an XOR. And that's it. So this block only takes 2 gates to build. Takes an AND gate, takes an XOR gate. Now we don't have to do that, right? We could have made our big full adder and just used one of them over here and tied the input to ground, but it's got all this hardware inside, right? This block, very, very simple to build. So we want to use one of these here, and these are all going to be our regular full adders. But this is going to be a special block. So this block is called a half adder. And that's what we're going to use here. And that's going to be a pretty efficient way to build a 2-bit adder. So you'll get a chance to go through all of this again in your next lab. Okay, you're going to look at the truth table for a 2-bit adder, and then you're going to think about designing it with a pair of half adder, full adders. And then you're going to do the truth tables for those, and you'll do the simplifications, and you'll write equations and come up with circuits, and then turn that into a wiring diagram, and you'll actually build this. And you get something that can add 2-bit numbers. Okay, so this is kind of a preview, first view of that, but next week's lab you'll get to do it all again.
Question.
Yeah.
So except for the original half adder, is it possible, and well, I'm sure we'll find out later, to just create a circuit using one full adder logic block and just feeds into itself? So it takes in a carry, creates a carry, moves a carry back, then hits a carry again, inputs a sum, and just
Yes.
repeats itself over and over again.
Yes. And pretty much the second half of the course is all about those kinds of circuits.
Okay.
So those are things that we can call state machines. And they're more complex than just here's the inputs, here's the outputs. Their behavior kind of depends on what's happened in the past. And that's an excellent example of a state machine where you would just have one adder and just shove the bits in one pair at a time, take the sum out, get the next bits, and so on. And yeah, you can definitely do that. And it's not a bad approach to doing addition. And if you think about what's inside your computer, you may have a 32-bit adder or a 64-bit adder. You probably don't have a 1,000,000-bit adder built into your CPU. Okay, but your CPU can add 1,000,000-bit numbers. How does it do it? Well, it would do it, say, 32 bits at a time. You can write a program. And when you write a program to do something, really what's happening is exactly what you're describing. You're using a fixed piece of hardware, but you're continually changing the inputs, taking the outputs, doing something with those, feeding them back in, and looping through like that. And where we're heading in this course is basically an understanding of how we could build a computer. Right? And we can't do it just with truth tables, because truth tables are static. I mean, we could, but we don't. But everything we're doing right now with truth tables and logic gates and simplifications and so on will go into building memories. And once we have memories and logic, we put those together, we get state machines. That's basically what a computer is. And we're only about 2 weeks away from that. So this will all be worth it. Bless you.
Thank you.
All right, other questions? So what about subtraction? We have to do this all over again to make a subtractor? It's been 2 classes. Invert it. Explain.
Change the zeros to ones and ones to zeros.
Change the zeros to ones and add the ones to zeros. Okay, what will that do for us? I like it.
Give us the opposite of addition.
Okay. It'll give us the opposite of a number. That's not quite enough to do subtraction, but it's really close. Add 1, why?
Because the other will add on.
Yeah, 2's complement, right? So we learned 2's complement and we said we can represent negative n by taking n, complementing all the bits, and then adding 1. So here's an idea. Suppose you have an 8-bit adder. You buy this at the store, it's yours, okay? You don't have to build it. And we have 2 numbers a and b, and we want to calculate a minus b. Well, if we could take b and turn it into minus b, we could put those into our adder, add them together, and we'd get a minus b. Because that's the beauty of 2's complement. You can add the negative, and it's like subtracting. So to get the 2's complement of b, we can basically take b and in some way run it through an inverter. Now b's got a bunch of bits to it, but I can do my little trick of drawing a diagonal line with an 8 to say I've actually got 8 lines here and 8 inverters. So I'm going to invert every bit, and then I'm going to put this into another box which says +1. And it takes that 8-bit number coming in and it adds 1 more to it. I'm going to send that into my B input. And A, which is 8 bits, I'm going to send into my A input. And my sum is going to be A minus B. So if I have an 8-bit adder already, which we just built, I can make myself an 8-bit subtractor by simply changing B around. Now, inverting each of the bits is pretty straightforward. It's just 8 inverters. What about this +1 business? How do we add 1 to our number B? It's not immediately obvious, right? Because if there's a bunch of 1s in the beginning, when you add 1, we're going to get a ripple carry that moves over. It seems like we need another 8-bit adder, right? But we don't. Say again?
Just the half adder.
Just the half adder. Although, if we tried to add 1 to this number, right, we need to somehow get that 1 that carries out of here and ripple it all the way over to here. Well, we can do something with this half adder. Suppose I make this a full adder again. Forget about the half adder thing. So you've got a full adder, and normally we put a 0 in there. What happens if I put a 1 into that first full adder's carry in? Right? I've incremented my sum by 1. So I'm going to get rid of this. I'm going to take my inverse of B and just feed that into my B input, but I'm going to change my first carry in to be a 1. That's going to effectively add B complement +1 to A. There's my subtraction. This is a trick. There's no reason this should be available to us, but it happens to be available to us. So we're going to take advantage of it. All right. Alright, so let's see a really sneaky design that takes advantage of this. And let's just make a 4-bit adder subtractor. So these are all full adders again, including that rightmost one. The carries ripple. We'll just make that last carry out available if somebody wants it. And we have a pair of inputs on each. So this is A0, A1, A2, A3. And up here I'm going to have B0, B1, B2, and B3. Alright, here's the trick. Sometimes I want to feed B into my adder. Sometimes I want to feed the complement of B into my adder. And I don't want to have to rewire my circuit. So this is another thing that XORs will do for us. Take a look at this output compared to B. And in some cases, the output is exactly the same as B. And in some cases, the output is the complement of B. And what's determining whether the output matches B or matches the complement of B? It's the value of A. So we can think of an XOR as some kind of controllable inverter. We can think of it as a box that looks like this. It has an input B, it has an output, and it has an invert command. And if invert is equal to 1, this is the inverse of B. If invert is 0, this is exactly equal to B. And the way we build it is just an Xor gate. But from a system level diagram, we might say this: if invert equals 0, out equals B, if invert equals 1, out equals B bar. So hold that idea. Let's finish this up and then we'll take a break. So I'm going to hook up some Xor gates. To feed my B inputs. But this other input on my gates, I'm going to feed that from outside. So if this line is a 0, this is just taking B0 and passing it to the output. B1 gets passed to the output, B2 gets passed to the output. And I'm just passing B into here. And I'm also going to take this line, I'm going to feed it to the carry in on this first full adder. And so I'm going to call this function. And here's what function does. So a function is equal to 0. Let's trace through this. We have 0 going into each of these XORs, which means the output of the XOR is the same as the B input. So B is coming into our full adder unchanged. This is taking A and adding B together, and since our function is 0, our first carry in is 0. This is just plain old addition. So S equals A plus B. What happens if function equals 1?
Two complements function.
The 2's complement of B comes into here, while the inverse of B comes into here, and a 1 goes into that first carry, which means the sum is equal to A plus the inverse of B plus 1, which is A plus the 2's complement of B, which is A minus B. So you throw this whole thing in a box, and it's like an adder, but it also has this extra input that if I set this input high, now it's a subtractor. If I tie this to ground, now it's an adder. And you get 2 for 1 basically, because there's not a whole lot of extra hardware in here than the adder itself. Okay, so that's a huge example, right? That's a lot to process. Okay, but think about it in parts, right? When you're looking at this later, think about 1-bit addition. Think about full adders. And we can do all of the truth table stuff and everything like that that's associated with getting a full adder. Or we can think of it logically. What is a full adder? We can think of it in terms of its system diagram. 2 bits go in, a carry goes in, a sum and a carry come out. And if we're thinking of it in that sort of behavioral viewpoint, it makes sense to put these together and get a 4-bit adder. And if we think of this block as a single 4-bit adder, then it's not too bad to think of inverting the input and adding 1 to make a subtractor. But if you were faced with the circuit diagrams for each of these and this stuff, there's very little chance of looking at that and figuring out what's going on. Right? So we're modularizing. How many people here are computer science? Okay, so this is the heart and soul of computer programming, right? Modularization, code reuse, right? This is a hardware analog to that. When we need to create a full adder, we've got to understand what's going on in here. Truth tables, K-maps, etc. When we're using a full adder, we can think of it from this sort of box point of view. Inputs, outputs, what does it do? Without worrying about how it does that. And once we have an adder subtractor, we can put that in a box and we can say, here's your adder subtractor. 4 A bits, 4 B bits, 4 some bits coming out, and a function input. And we don't have to know any of this to be able to use that to build, say, a multiplier, which is just a bunch of additions. All right, so let's take a 5-minute break, come back at 1 o'clock, please, and we will take this one step further, and then we'll switch gears. And I'm going to fix my screen resolution because it is low.